In this example, we're going to look at how a car or a bicycle goes around a bend, a circular bend, on a flat road. Now, why do we say flat road? Well, often off-ramps are kind of like NASCAR turns where they angle the road, so you're actually on this little velodrome type of an incline, and it's helpful. I mean, that's why the race cars and I say the NASCARs have the turns are angled, or the bicyclists in their velodromes have these angled road beds themselves, and we'll see why that's the case in our next lesson. So let me erase this because this is not what we're looking at right now. So we're just looking at a flat road. So if you were looking at the car coming at you, we would be seeing the view that's shown up top on the left here. We have mg pointing straight down. We have the force normal pointing straight up. And we're going to see that the only possibility for a radially inward force is the frictional force. So the friction between the tires and the road provide the radially inward force on this circular bend to be able to go around the bend without skidding out of control. Now, the numbers we're given to look at here I think will be helpful in terms of your understanding, so let's go look at that. They give us a 1,000 kilogram car, so we have a 1,000 kilogram car. The road is flat. The radius of curvature of the road is 50 meters, and we are told that the car is moving at 14 meters per second, and we're being asked, will the car be able to go around this bend, or will it skid out of control? Under two specific conditions. One, when the tires and the road are dry, and we have a coefficient of friction of 0.6, and on another day, when it's icy and slick, and we have a coefficient of friction of 0.25. So let's take a look at what we have to work with here. So the view that we're looking at, by the way, here in this picture is just a top-down view where the frictional force, like we show above, is in the radially inward direction. Well, I'm going to focus on this force diagram in setting up my equations. In the y direction, as it's shown here, we want no movement. We don't want the car sinking into the ground. We don't want it bouncing up off of the ground. So sum of the forces in the y direction equals 0. Force normal minus mg equals 0. So in this case, the force normal indeed equals mg. We don't have a whole lot to analyze in the radial direction because there's only friction. So friction is our radially inward, which we designate as the positive direction. Mu times the force normal then is our frictional force radially inward equals mv squared on r from our circular motion requirement for the acceleration. And we're just going to do some simple substitution. We're going to substitute in mg for the force normal, so that's where the mg down here comes from, mg in for force normal. So we can get mu times mg equals mv squared on r, and look, the m's cancel out, and that's a good thing if you think about it, because all they're going to have to post is a speed limit for the road, not a mass requirement. So it doesn't matter whether you have a large truck or a small light car, mass will not come into play in terms of the maximum speed you can go around the bend with. So this is the equation that is going to govern the design of the road. So how the coefficient of friction here matches with the speed here and the radius of curvature of the road here, this equality tells us the balance that we need between the speed, the radius of curvature, and the coefficient of friction. Well, in the problem we're looking at, they gave us a coefficient of friction on a dry day of 0.6, and all I've done here is take that boxed equation, or here, take that boxed equation and solve it for the v squared. So if I plug in 0.6, 9.8, and the radius of curvature they gave us was 50, we can solve for v, and notice I put max there. So the maximum speed you can have is 17.1 meters per second, and this equation will be satisfied. So anything below 17.15, right, you're safe, and since we're at 14, we're safe. Well, that changes if we put in a coefficient of friction of 0.25. So on a wet day, if we have 0.25 in for the coefficient of friction, g is still 9.8. The radius of curvature is still 50. Notice now we have a Vmax of 11.07, and if we are traveling at 14, we cannot maintain our circular motion. So this governing equation that governs the circular motion, the v squared on r with the coefficient mu, would not be satisfied at 14, right? So it would be an inequality at that point, not inequality. So this is how we handle cars on flat embankments, flat curves, roads. In the next lesson, we're going to see that velodrome example, that car on an embanked incline, which is more typical of what we see. Like if we go off the off-ramp of the highway, they embank the roads. We'll see that that is very helpful to keep cars going in circles, even on wet or icy days. But we need to understand the flat road before we can go on to the more complicated problem. So there you have it.